Hello, everybody, and I'm sad to hear that this is going to be the last one. But I know we'll all see each other again. I still owe you all an ice cream party. I haven't forgotten, and I won't forget. But I wanted to remind you again that this was the session where I answer all of your questions. I have a lot of stuff I can talk about already, but I really, really, really wanted to make sure that all of you got all the questions you wanted answered. And I told you it could be about any topic in particular. But it turns out that as far as getting questions to me ahead of time, the first question I got was from Rainey and Rose, and it involves talking about planet Venus and the greater concept of these mathematical patterns that we see all over the place in nature. So let me just go right to the email that they sent me, because I've got my answers ready to go. So they asked about the five-pointed pentagram shape that you see in the patterns of Venus, to remind you what we talked about last week. And you wanted me to give a little more detail about that. So I'm willing to do that. As a matter of fact, you also asked about retrograde. Now, if you think about this, if you've all heard of retrograde, this is a term that goes back to astrology when people were using the planets to predict the future. And retrograde is not that different from if you know retro. Like if some of you young folks are dressing in 1980s style because you like Stranger Things, you could be said that you're following retro fashion. Retrograde means going backward. And just to explain, when you see planets in the sky like Venus, usually they're moving from west to east through the stars. So it will be a little bit farther east every night. But occasionally, a planet will do a switch in direction where it will start to dip back towards the west. And if you were to plot that course over a long period of time, it always looks like a loop-de-loop. Go ahead and ask your question. Is it Rainy or Rose? Did you have a question? Oh, because this is for you. I hope you're paying close attention. This is all right for you. So let me go back to that diagram I showed you from the old astronomy book about Venus and those crazy things that Venus does. Hold on, let's find that picture here. Hope you can all see that. So, excuse me. If you look at the loops in the center that make part of the star shape, that loop is actually the time when Venus does a retrograde. So try to imagine following that as a path of motion, and it looks like it was going one direction, and then all of a sudden it goes wee, and it goes the other direction. Now, what did the ancient astrologers think? They thought that when a planet was going retrograde, it might signify that all of its meanings were reversed. So since Venus is associated with love, when Venus is in retrograde, maybe hate, the opposite of love, antipathy, is dominant. And then luckily that doesn't last very long. So it goes back to the normal direction. Everybody says, okay, love's back in style again. Okay, I obviously don't think that those things are true, but this gives you a window into the mind of an astrologer trying to make a prediction of the future based on the motion of the planet. They used to associate that retrograde motion as having a strong significance. But I want you all to think about this from a modern day astronomy point of view. What could possibly be causing Venus to look like it's reversing direction in the sky? Is Venus actually switching directions temporarily? Or is something else going on? Hold on, I'm going to stop the share. And I want to hear going down.
Slowing down.
Well, this is another problem that is hard to understand unless you remember that we live on a moving planet. And if you were an ancient astrologer in Greece or Egypt thousands of years ago, you probably did not think that the Earth was a moving platform. So you assumed that Venus was the one doing all of the weird movement. But think about this. Okay, I'm going to give you an example that might actually help you understand this. Think about where Venus is in the solar system relative to us. It's on an inside lane. it's closer to the sun than we are. So that means it's moving faster than we are, right? And imagine being in a similar situation where, let's say you're in a car that is on the fast lane on the highway, and there's a car that is in front of you on the right hand side, the slow lane, let's say. And let's say that as that car, if you look at that car in the distance, I'm trying to approximate this. If you can look at me in the picture, if I'm the car that's in the background and this car's in the foreground, as I drive, if let's say I speed up and I get faster, this car is going to look like it's moving in one direction. It's going to be looking like it's still moving the same direction as me, but as I pass it, what direction is that car going to look like it's going as I pass right next to it?
Backwards.
It's going to look like it's going slightly backwards relative to my speed. But when I look at it from far away, I'll say, oh no, it's definitely still moving forward. That guy didn't go into reverse. What happened is that I passed them in the car. And for that time that we were side by side, if you looked out the side window, there would have been this optical illusion that the car was moving backwards when you know it's still moving forward. It's just moving forwards less quickly than you are. Does that make sense? If that makes sense, then let's compare that to the planets. In this case, Venus is the faster car. We're the slower car. And we are now, put yourself in the perspective of the other car that is coming from behind you. So Venus is moving around the sun, and we are also moving around the sun. And when Venus passes by us, it looks like it's reversing direction, and then it resumes its normal course of direction. Of course, the crazy thing is that the way I've described it as cars is a little confusing because this is backwards. Venus is going east, and then it looks like it switches to the west, and then it's going east again. And Venus is the faster car in this situation, but other planets do retrogrades. When Mars does a retrograde, it's because we are the faster car passing Mars on an inside lane. But other planets like Saturn, Jupiter, and Mars do retrograde very seldom because of their longer orbits and the fact that we don't, pass them that quickly, about once a year, whereas Venus has a shorter orbit, so we get to see more retrogrades per year. And if you actually remember how many you get, if you look at that picture, you get 5 over an 8-year period with Venus. So Venus does it so dramatically, it's so bright, it's so visible. And if you pretend every one of those loops is a retrograde, then you can actually try to imagine Earth and Venus. Let me go to the next picture. Oh, the one before, I mean. Okay, here's another way to understand the retrograde from an observational point of view. On the top picture, do you see where it says 456 for April of 1956? And then you can see as we go forward in time, it goes 5, 6, 7. Follow the line that looks close to flat. That line that looks like the shape of a canoe in the foreground, that's the retrograde portion of Venus's travel. And then as you see the line go to where it says 10, and then it starts to go backwards, that's actually resuming the normal course of Venus. And you can see many more months in that period. It goes from 10, 11, 12, then January 57, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it spends a long time going that way. In this picture, it spends most of its time going from right to left, which is in the sky, going from west to east. And then it spends a short time doing the retrograde, which is going from east to west. Does that make sense? Do you see that? It's in this picture. It's not that obvious. But if you look at the spacing between the numbers, the big spaces means Venus is moving quickly relative to the observer. And the small spaces between the months mean it's moving slowly. So can you turn that picture into that loop-de-loop that's part of that diagram? If you can visualize that, then you'll understand how that picture was made. So that was just one of the loops. And you can see on the bottom picture, there's another loop again. So this time, well, I think I don't want to get too much into that particular detail, but I think you get the idea. The reason why planets go backwards in the sky is not because they're going backwards, it's because we're passing them, and they're passing us, and that illusion creates that backwards movement effect. So Now, you folks also had a separate question about Venus, Rainey and Rose. You asked not just about the retrograde, but and also that pentagram flower. And if you want me to explain that more, I will. The five-pointed star thing. But basically, it is what you see if you track where Venus is amongst the zodiac, like how it moved through Taurus recently, and then you map that with the zodiac in a circle. You'll see that pattern, something that astrologers often did in ancient times. So that's how you get that. That takes about 8 years of observation to make. But imagine how you would feel if you spend 8 years, doing that little plotting. And at first it would look like nothing. At first it would look like a bunch of spaghetti noodles. And then all of a sudden, 8 years later, you're like, wow, look at this pattern. It would feel like you just encountered something sacred or holy, like you just discovered a magical property of the universe. Well, that's not the first time that humans have encountered this. Think of a snowflake. Have you you have an opportunity to see them right now. Go outside and catch one. Everybody knows snowflakes make amazingly intricate designs, and those designs look like they were something imagined by an artist or a graphic designer. They're so impressive. They look like precision. They look like machined parts out of some sculpture. But actually, that pattern just emerges out of a mathematical pattern that goes down to the very basic water molecule. And I don't know if you guys remember this app. I don't know how to show it, share it on Zoom easily without just putting it up on the screen. The molecules app that I've used many times before when we talk about chemistry. If you go on there, I'm going to show you something really cool, really quick. We've talked about carbon dioxide, and let's look at that molecule. It is just 3 atoms. Carbon is the one in the middle that's black, and oxygen. Oh, you can see all the dirty fingerprints on my iPad. Ugh, how gross. Well, so trying to do this without a double reflection, but I think you get the idea. You can see that wiggling molecule, but that's CO2, okay? We've talked about CO2 plenty, but what about H2O? H2O, do you notice that it's not straight? It is bent like a V. The hydrogens are the 2 white ones on the outside, and the oxygen is the red one in the middle. But this is a challenge for those of you looking at this. Why do you think those atoms aren't in a straight line like in carbon dioxide? Or does this look like a picture that's incomplete? Is there something missing from this picture that would make it nice and pretty and symmetrical? Go ahead and weigh in, kids. I want to hear somebody give it a shot. Why do you think CO2 is flat versus H2O being V-shaped? They're both 3 atoms.
Some are heavier than others or something.
That is also true. That's a good guess. Now, I feel kind of like a meanie asking this question because it requires that you understand how electrical charges are distributed on an atom or how electrons behave. Not going to expect that from you guys, so I'm not going to spend much longer. I'm not going to agonize you with a long wait to get the answer. But what is happening here is that hydrogen and hydrogen, they are very small atoms. They have 1 electron and 1 proton. And when you are built into a molecule like these atoms are, you've got to share your electrons, which means that since oxygen is such a big atom than hydrogen, when hydrogen is sharing an atom with oxygen, the majority of the time, that electron isn't with hydrogen anymore. It's like you let your friend borrow your puppy and it spends more time at your friend's house than at your house. It comes back home for food, but then it goes to your friend's house for the rest of the day, and then it comes back to your house again for food, and then it leaves and goes at your friend's house. So while the puppy is hanging out with hydrogen, while the electron is hanging out with hydrogen, hydrogen is neutral. But since the puppy, the electron, is usually hanging out with oxygen instead of hydrogen, what would that make hydrogen's electrical charge? Come on, guys, protons, electrons. You take away the electron, you've got only a
Positive.
proton. Yes. And what do positive charges feel about each other?
Not good.
Wow, they repel each other. So this weird arrangement of the water molecule is the only way you can fit these atoms together without their positive repulsive charges causing them to fly off. So it's sort of like a happy compromise that allows them to be close to each other, but their positive charges are actually deflecting them. And there's, oxygen right here. It has an extra negative charge because it has an extra electron two extra electrons that is borrowing from the hydrogen. So when hydrogen's puppies are playing with oxygen, oxygen is negatively charged and hydrogen is positively charged. And not to get too far into the chemistry, that's why water has a lot of properties like surface tension. And that's why water sticks to your fingers. It's actually slightly magnetic. There's hydrogen bonding, and there's also van der Waals effect that explains why if you put your finger on the surface of a glass of water and you pull it up, the water rises with your finger, it sticks a little bit. And this is partly due to this strange arrangement of the atoms down at a level that you cannot see. But I also want you to think about this arrangement for another way. These are like Lego blocks. There's only certain ways that they can fit together. If you think about the more negatively charged oxygen atom and the more positively charged hydrogen atoms, how many ways could you fit something like that? It's like magnets. If you put them together in the wrong way, they repel. And if you put them together in the right way, they stick. So can you imagine in her mathematical mind? And because Rosie and Rainey's question involved fractals, which is another concept that they included in their question that this is all about. If you take a bunch of these little molecules and stick them together, there are only certain patterns that you can make. And generally speaking, those patterns tend to be triangular or hexagonal, because a hexagon, is just like a bunch of triangles put together if you think about it. So think of, 6 triangles stuck together, you get a hexagon. And think of how water molecules are kind of a triangle on the molecular scale. And you stick all those triangles together, you get triangular shapes that stick together and become hexagonal shapes. So water doesn't have a choice into how it can make these crystals. This kind of crystal patterning is the same reason, why other things happen, like why certain rocks break under, in certain directions along grain. It's because of how the molecules are stuck together. And speaking of rocks and hexagons and patterns in nature, to address Rainey and Rosie's question, there's a lot of people who, when they see these patterns in nature, think that it's somehow proof of some kind of intent, like this was made this way. It was intelligently designed to look like this. But that is not how I interpret this information. When I hear about these things, I look at it as that's the power of math. Math and numbers, they manifest themselves in all kinds of ways. And I'm going to show you a cool combination of hexagons that come from completely different places, one on another planet, but they're all based on just mathematical tendencies and probabilities and how things fit together in the easiest way possible. Because nature is lazy. Nature doesn't do things the hard way. It usually follows the easy way, especially when it comes to chemistry. Molecules only have so many ways they can fit together, but the most likely way is the way that they're going to follow. And so let me ask a question. Have any of you kids ever heard of a place in Ireland called the Giant's Causeway? It's in Northern Ireland on the coast.
No.
We have a piece of that causeway at the Fairbanks Museum in our collection. But when you look at the piece that we have, it's a piece of rock that looks like it was carved to be almost a perfect hexagon. Almost. Not perfect, because nature doesn't do things perfectly all the time, just most of the time. And that's how evolution goes wrong. So let me show you an example. I've got some cool pictures of something that you're going to want to learn as a concept. It's a word called tessellation. And it has to do with how you put tiles on the ground. Speaking of tiles, this might look like tiles to you. I hope you can see this picture. Is that picture clear for everybody? This is the famous Giant's Causeway. Now, according to the local legends of the Irish people, this was a road built by giants. And I mean, you can see why. Look at how those cobbles look like cobblestones on a giant road. We have one of those columns that has that hexagonal shape. And if you look carefully, you can find ones that are perfect hexagons, but you can also find ones that are imperfect, ones that are not completely the six-sided or evenly symmetrical. But let me show you some other pictures because this is not how the Giant's Causeway always looked. This is a product of volcanic action combined with how things crack when they freeze, combined with erosion over a long period of time. And with that recipe, you get a beautiful landscape that looks like it was made by a mathematician. Now, this is what the Giant's Causeway might have looked like before it looked like that. This is pahoehoe, I think is the way you pronounce it. That's the native Hawaiian word for this kind of lava. Lava that flows out in an oozing slow motion fashion. This stuff comes out really hot, but it like imagine pouring something like wax into a valley and letting it settle in, pouring it slowly, and then it's still hot. So what you're seeing at the top of this picture, is the top layer has frozen already. It's like a thin skin. Have you ever had hot cocoa and you let it sit too long and the top layer solidifies into that gelatinous sheet of butterfat on your cocoa cup? Well, think of it like that. This is like a thick frozen layer of lava on top, but underneath that rock, a lot of the lava is still molten. It is like a loaf of bread that comes out of the oven. The core is still hot while the outside is cooling down quickly. So basically, let's imagine that you have this loaf of lava. The top part freezes quickly because the air cools it down, but the inside freezes very slowly. But what happens as it freezes, unlike water, which actually expands when it freezes, most materials shrink when they go from liquid to solid. So basically, the stuff on the top is shrinking as it cools and hardens, and the stuff underneath has not shrunk yet. It's still large. So basically, there's a pressure, and it causes the top layer to start cracking to accommodate the fact that there's a difference in pressure. And that cracking will follow the path of least resistance. And the path of least resistance with many materials causes it to break into this hexagonal pattern. This is based on a concept called tessellation, which is how to break up a surface into subunits where there's no space left over. You don't have any extra material. You don't want to have any extra room left over. So how many ways can you break up a surface into units that will cover it completely without having any bits left over? If you were a person who does ceramic tile work, that's your life. You're doing tessellation. You're filling over a surface with small pieces, making sure that there are no empty spaces left over. And let me just show you something real cool. This is what you see if you stand at the bottom of the cliffs made by the Giant's Causeway. Can you see that the cracks that originally started on the top layer moved down the rock as the rock froze and the cracks were preserved? So the cracks that started on the top continued all the way down to the bottom of that big mass of lava. That's the big loaf of lava I was talking about. But do you see, it looks like that section got covered up by something else, and that's what preserved it from getting totally eroded. But this part, can you see how those columns have been breaking down over time? Probably the waves of the ocean and ice in the winter and wind and all that weather that they have in Northern Ireland with all the wind storms and wind and waves. Those rocks have been breaking off, and when they break off in perfectly or almost perfectly hexagonal chunks. So we have one of those chunks in the museum, a chunk of the Giant's Causeway. And that's not the only place in the world where this weird mathematical pattern has emerged. When I was a kid, my dad took me to a place called the Devil's Postpile in California. Oh, here's the Giant's Causeway, by the way. I had one more cool picture loaded up. See that? Can you imagine that before this broke into different layers, it was actually all one flat layer? And then maybe the ones closest to the ocean, most exposed to the water, were the first to break off. So you have this ramp shape that looks like it's made out of tiles or cobblestones. Does that look like something that was built by an intelligent being?
Yes.
If you were a person, yeah, I mean, if you lived thousands of years ago, I wouldn't blame you for thinking maybe there was giants that used to live here in Ireland and they made these giant highways and these are the ruins of their ancient world. I don't blame. That's cool. That's a really cool idea.
Are
We
these
don't. Yeah.
on display at the museum? Or is the one on display at the museum that you have? Oh, okay.
It's right on the floor. It's
So how big are they?
Oh, the one that we have is about 3 feet tall and about this big around, like Leila's saying. And you know, it's like the size of a bed stand by your table, you know, by your bed, like a little nightstand, about that size. And that's what one of these would look like. I don't know, you know, I don't think you could legally get one today, but back in the 1800s, I'm sure Franklin Fairbanks was able to get one sent to the museum. It's now a park. It's actually closed to the public right now, but this is a national park part of Ireland. It's actually Northern Ireland, so technically it's in the UK. It's in Britain because of Northern Ireland. I'm not going to get into all that politics, but it's in Britain, so in Northern Ireland. However, yes, we have one. So when the museum opens up, if you haven't found it, it's on the main floor. It doesn't get a lot of attention. It kind of looks like it's just sitting there. It doesn't have a great sign on it. So you might have to hunt for it, but let me know if you have trouble finding it, when we ever do open back up, and I'll show it to you. But I have not been to Ireland myself. I have ancestors from there, but I've never been to Ireland. So when I was a kid, my dad took me to a place in California that looks a lot like this, but it's not on the coast. Up on the Pacific Crest Trail in California and the Sierra Nevadas, there's a place called the Devil's Postpile. Now, isn't that funny? What was the name of the last mountain I was talking about last week? Devil's Tower. What is this? Naming weird things after the devil? It must be the devil that did it. Well, do you see what I'm talking about? Giants, Causeway, intelligent beings must have done this. The devil, evil but intelligent being, must have done this. So when people encounter these patterns in nature, it is a tendency that we think it must be an intentional design. But really, it's just like a snowflake. It's something that happens as a course of nature, as the nature of the materials, the nature of temperature and physics, and the nature of how crystals form. Something that is invisible to us, an atom and a molecule, can make itself be seen on the macroscopic scale because of these patterns that build up with large numbers. So this is a really cool spot because look at this. This is what the Giant's Causeway would have looked like when it first started cracking. This one is more recent, and erosion, because this is not on the coast, hasn't been as dramatic. So you have a section where you can see the actual flat surface of what was lava. Can you see that in the picture? And you can see how it started cracking, and then the cracks are continuing further down. And there's why they call it the Devil's Postpile. From the side, it looks like the devil was going to have building a wall project, so he needed posts to build his wall. And here are the devil's posts for building the devil's wall, supposedly. So that's the logic of the old-time California settlers that named it the Devil's Postpile. But this is tessellation in nature. So let me show you a website real quick that I found. It's called Math is Fun. And on mathisfun.com, they have a really cool introduction to tessellation. And you can see rectangles, a brick wall, that's tessellation, right? But that's designed by people. Regular tessellations are one where there's only one shape involved. And there's only 3 possible regular tessellations: triangles, squares, or hexagons. Those are the ones where it's the same shape repeated over and over again. And can you see how the Devil's Postpile and Giant's Causeway is an example of regular tessellation with a hexagonal pattern? And so if you want to get more into this tessellation concept, If you've ever looked at the artwork of MC Escher, any of you fans of MC Escher, I loved his artwork since I was a kid. He used to love to play with the concept of tessellation to create all kinds of optical illusions. And so that's one artist that you can use as a tessellation touchstone. But this is the website, Math is Fun. And this is a great way to understand this concept. Okay, so let me go to a completely different hexagon. Now, you guys know what the Fairbanks Museum's logo looks like, right? It's a hexagon. And I wasn't involved in choosing that particular logo, but when it was chosen, I said, this is a great pattern. It's the honeycomb. It's the snowflake. It's the columns of the Giant's Causeway. This pattern appears in nature over and over again. Maybe this is why the Greeks thought that 6 was a number that was holy, the hexagon. We could talk about Pythagoras and the significance of 6 and 12 in the ancient Greek world. But let me show you a completely different hexagon from a completely different planet. Does anyone know what this is? I'll show you that this was made possible by a mission that is now just ashes in the atmosphere of the planet that it studies. The Cassini mission, which has burned up now in the atmosphere of Saturn. Look at the picture here in the background. This is actually the North Pole of Saturn. And what do you see?
Do you see it? That's so cool.
Yeah, there's pretty much nothing cooler than this as far as I'm concerned. Like the fact that we think about all these patterns and how they happen on Earth, and we're talking about little rocks and little snowflakes. And here we have an entire planet that is hundreds of times larger than the entire Earth. This is a storm that would be the equivalent of the polar vortex that we think of on the Earth. The constant swirling of winds that happens because of our planet's rotation. On Earth, it's a minor thing relative to what it is on Saturn. Saturn is big. Its atmosphere is all that it is. It's all air. And it has wind speeds that can go up to 1,000 miles an hour, especially near the equator. So Saturn is bigger and more gas, more air, crazier variations in pressure. The difference between, the air pressure at the top versus at the bottom is a mind-blowing difference. So you have a lot of different things going on Saturn than you have here on the Earth, but you still have gravity. You still have a planet rotating, and you still have, daytime and nighttime, which is weird on a gas giant. And Saturn has an orbit around the sun that takes almost 30 years to complete. So everything on Saturn is out of proportion compared to the Earth. But still, you've got gravity pulling gases down. You've got rotation making the gases swirl around. And because on Earth, our hurricanes can't get this kind of thing because there's too much competition. There's other things going on. The hurricane only lasts for a few days before another cold front comes in, blows it up, and the hurricane only lasts for days or weeks. But on Saturn, you have a stable storm that, as far as we know, like the red spot on Jupiter, this storm also may be centuries old. It's probably always there. So it could be millions, if not billions of years old, a constant storm that is the shape of a hexagon. So maybe you think this is proof of aliens, but I just think it's proof of the majesty of mathematics. And I know Leila's gonna laugh when I say this, but there was a 1950s cartoon called Donald Duck in Math Magic Land. It's very hokey and very corny, and I know Leila's laughing now because, there's some very outdated concepts in there, and they spend way too much time talking about billiards. Nobody that I know plays billiards. So it's not going to be the most engaging thing you will have ever seen. But if you ever get a chance to watch Donald Duck in Math Magic Land, it was a Disney cartoon that showed how many times these patterns appear in nature. And my particularly favorite part is the part about Pythagoras and the Pythagorean theorem, and how, it actually doesn't talk about the Pythagorean theorem as much as it talks about how the 5-pointed star, the pentagram, remember Venus making the 5-pointed star in the sky, was actually the symbol that was used by Pythagoras' group as to identify themselves. That was like their logo. Like, hey, I'm in the Pythagoras club. I'm a Pythagorean. Look at my star. And that star inside of the 5-pointed star, the same star that we have 50 times on our flag, that star, if you take that little pentagram, you can use it to discover all kinds of other cool mathematical relationships like the golden ratio called phi, which we know in Greek words, just like we know pi, which is the circular radius and circle, circumference and radius relationship. So the ancient Greeks, people like Euclid, people like Pythagoras, people like Archimedes, they all contributed in an enormous way to what we consider modern mathematics. And their fascination with mathematics came from looking at things in nature, like Venus, like stars, starfish, snowflakes. And that's where they got the passion to try to break down the numbers. And even music. Pythagoras loved music, and he mathematically figured out the things that we think of now, like major scale, the minor scale, and the relationships between chords, like a first and a fifth. If you play the blues, a 1-4-5 progression, all of these weird mathematical concepts that are hidden in music, it was people like Pythagoras that helped uncover them. So that is why so much of our mathematics uses Greek letters like pi and phi. So what do you think of that? And one more thing, unless anybody else starts weighing in on more questions, I see a question coming about Saturn and Jupiter and the moon making a smiley face. Let's see if we can reproduce that. If that happened, it would have had to have been in the early morning hours when I was probably snoring. So I can use Stellarium to reconstruct that, because I do believe that that could have happened when the moon was in its waning crescent phase, rising in the early morning. Right now, we're in a new moon, and that would have been a couple days ago. So hold on. I just want to talk about Venus again, but in a different light. So hold on, I'm going to share a different screen. All right. So remember, Venus, as beautiful as it is in the sky to our eyes, is a planet unto itself. And that planet is the hottest planet in the solar system. This picture on the left is an optical picture of what you would see with your eyes if you were riding on board the Venus Express. It took a regular picture, and you can see the thick cloud layer. But you notice that the cloud layer is not completely uniform in color. It has a little bit of gradation, a little bit of stripes, and those clouds are mostly made out of sulfuric acid, H2SO4. I'm going to sound macabre, but have you ever heard the rhyme? My 6th grade teacher made me memorize the recipe for sulfuric acid just because of a rhyme. It wasn't because she was trying to teach me how to be evil, but something. Mary drank some H2O, but Mary is no more. But what Mary thought was H2O was H2SO4. It's a silly little rhyme, but H2SO4 is sulfuric acid. Can you see the difference between it and water? H2O, H2SO4 is just got that little sulfur added into the middle of a water molecule, got some extra oxygen, but that makes it so terrible. And everybody always thinks of Venus as like a hellscape, 900 degrees Fahrenheit. The picture on the right shows you an infrared image from the Venus Express of what Venus's clouds look like. That's the nighttime side, meaning that all of that light is not coming from the sun. It is coming from Venus's internal heat. So according to what I read, it wouldn't be that bright if you were flying around in a spaceship. That's exaggerated to show detail. But if you were to ride on the back of Venus Express and look at Venus on the night side, it wouldn't be pitch black. It would be glowing dull red, like the coals in your fireplace when the fire is close to going out. And that's close to the temperature of Venus's atmosphere, 900 degrees Fahrenheit. Would you stick your hand in a bunch of red coals? Would you want to land on this planet?
No.
Yeah, I hope you didn't need to think about that very long. So just so you know, because of that atmosphere, the surface of Venus has always been kind of mysterious to us because we cannot see it directly with light. But a long time ago, the Pioneer mission in 1980, this is when I was a baby, when I was 1 year old, So the Pioneer mission went to Venus and using radar, basically by beaming radio waves into the clouds and waiting for the reflection of that radio wave, that's what radar is, they were able to map the surface of Venus, and they noticed that it had mountains, it had lowlands that could have been oceans, it had a varied landscape with a lot of volcanic activity. And, you know, to make a long story short, Venus could have been a planet that would have been similar to Earth as far as comfort levels for life. It could have been a just right for Goldilocks planet. But how do I put this delicately? Venus had all of its volcanoes go off at the same time. It's like it farted itself to death. It gave off so much gas. I knew that would get your attention. I know you would remember that now. Like, okay, hydrogen sulfide is one of the things that volcanoes give off, and sulfuric acid, all that too. Hydrogen sulfide is what makes a fart smell bad. So there probably was a time when Venus's atmosphere would have been so filled with fart gas, and that sulfur belch would have basically dominated the entire atmosphere. So it's like if Venus was like an Earth that could have been good, but it went bad somewhere in the recipe. The tectonic plates, the volcanic action did not result in a planet like ours, but instead it dumped way too much carbon dioxide into its atmosphere, a lesson for humanity, I hope. And it dumped way too much sulfur into its atmosphere, creating a greenhouse effect gone wild. So nobody thinks the Earth is ever going to be 900 degrees Fahrenheit, but you can see how carbon dioxide plays a role in making a planet hotter. Venus is the prime example of what happens when you have way too much CO2, when you can't cool down and you're 900 degrees Fahrenheit, whether it's daytime or nighttime. And that's all because of volcanic action and human activity creating pollution, carbon dioxide, sulfur dioxide. There's a lot of sulfur compounds in our pollution. We're hurting Earth's atmosphere in a way that makes it closer to like Venus's, which means we've caused our planet to heat up, not nearly to 900 degrees. But I hope you see the connection between carbon dioxide as a greenhouse gas and pollution here on Earth, causing our planet to get slightly closer to being like Venus because of our atmospheric changes. So, boy, oh boy, you asked a lot of good questions, Rainy and Rose, because now I'll show you one more picture of Venus of this sense. So, have we ever been to the surface of Venus? Yes. Here are the best pictures I could find from the Soviet Union's Venera missions. That's why you say Venus in Russian. And they sent these robots to the surface, which means that those robots had to parachute through all that thick atmosphere and land on the ground where it's 900 degrees Fahrenheit and is raining sulfuric acid. And what they found was a rocky, barren landscape. Not surprising. But the funny thing about these robots is that all of the Veneras were basically designed to be gigantic freezers. It was like an insulated box with a really strong refrigerating unit to keep the thing cold. And they basically, on average, lasted about 90 minutes on the surface of Venus. So they had an hour and a half or less to take pictures and make measurements of the atmosphere and the pressure. So a lot of the data we have from the surface comes from these missions. But it was very hard to design a camera that could take a picture in an environment that would melt glass and lenses. So you can see that they didn't get much pictures. But the one on the top is like raw data, but on the one on the bottom is filtered to more approximate the human eye. So just imagine being on that planet. Would you want to live there?
No.
Well, so to answer the last part of Rainy and Rose. Oh, you want to go? Somebody said yes. Aha. I hope you're ready for a hot vacation. But here's the one thing I want to say about Venus. You asked about the rotation. Well, Venus, when we're talking about retrograde, we're talking about how it looks from here on Earth. But Venus's rotation is also retrograde to what the Earth is, meaning it rotates in the reverse direction. So the sun on Venus would rise in the west and set in the east. But that does not really give you the full picture. On Venus, one day, even though it's going backwards, one day is 243 Earth days. So think about that. If you lived on Venus, when you see the sun rise, let's say you start counting then, you will see the sun in the sky for about 121 or 122 days. And then it'll set and you won't see the sun again for another 122 or so days. Does that make sense? So the day would be very long and the night would be very long, hundreds of days, over 120 days. But Venus takes only 224 days to go around the sun. So I've said it before, but those are the numbers so that you can, think of it for yourself. Venus takes only 224 days to go around the sun once, which is about 7.5 months. But it takes 243 days for it to spin once. So on Venus, days are longer than years. And why is that? Well, Venus is about the same size as the Earth. It's about 95% the size of the Earth. The reason why the Earth spins at 24 hours and Venus spins in 243 days in the opposite direction has totally, I need a glass of water. We're getting close to our break time, but I want to see if anybody out there can tell me. Does anybody want to explain or try to explain why the planets spin the way they do? It's really weird. For example, Mars is half the size of the Earth, but its rotation is 24 hours and 40 minutes. So close to ours. 24 hours here, 2440 on Mars. But on Venus, negative 243 days. And so does anybody have any notion as to what might cause these planets to spin the way that they do, why they have their own speed, and in the case of Venus, its own weird direction? Just think of what could cause that. Maybe if you played billiards, you would know. I hear silence. It's even quieter now. Is everybody Googling the answer? Come on, just think imaginatively. What now? I joked, but I wasn't totally joking when I said, think of billiards or playing pool. Have you ever played pool, kids? Hit the cue ball with the cue and
Yeah.
Okay. Have you ever noticed?
Did something knock into the planets, making them spin or do something? I don't know.
No. Wait, who said that? I couldn't see the name, but Sadie, is that you? You are right. So those of you who may have already studied this, you probably have heard about this before, but this is a picture. I'm going to show you. Let's see if I can get it on there for you guys. I'm going to share with you a picture that is a little pixelated. It's an old picture of what it might have looked like when the Earth was just forming. A day you probably wouldn't want to be here. This is an artist's rendition of what it might have looked like when Earth got smacked by something almost as big as Mars. And this thing that is almost as big as Mars has been given retroactively a name, Theia. And if you know Greek mythology, Theia is the mother of the moon. So when this collision happened, the debris, the stuff that you see squirting out on the sides of the crater that is being formed, became the moon. And before Theia knocked into us, it was a small planet. Think of like a smaller planet that was running on the same lane as us. And you just can't have that eventually. It's inevitable that the bigger one is going to cause the smaller one to crash into it or to get thrown out of that loop and make a new orbit. And in the case of this picture, Theia if actually, interestingly enough, I'm not going to get into all of this, but Lagrange points, we've mentioned these before. These are these cool gravitational anomalies that happen around an orbit. You can see where it says L5, that's one of the Lagrange points in Earth's orbit. And that is a kind of spot where it was able to sit for a while. But if you look at the middle picture, gravity started to play a little game with Theia, and it started getting a little too close to Earth. And eventually, Earth being larger won the tug of war. But it meant that Theia crashed into the Earth, and all that debris became the moon. And some scientists have shown evidence to say that it might be where the Pacific Ocean is, that material went up. The Pacific Ocean is the deepest ocean. So think of the Pacific Ocean as being a piece of the Earth's crust that's slightly hollowed out, as if it's missing material, and it's very deep. Is thinner and it's closer to the magma layer than other parts of the ocean. So maybe the Pacific Ocean is the hole that Theia excavated when it crashed into Earth 4.5 billion years ago, and the moon is the leftover byproduct. But then there's the other aspect. What happens when this is all over? There's no way to know what Earth's rotation was like before this event occurred, but as soon as it happened, have you ever played billiards where sometimes you smack balls together and they bounce off each other? Sometimes you give one a glancing blow and it'll stay in the same spot, but it'll start spinning really rapidly in the same spot. If you've ever seen a billiard ball, a pool ball do that, then you can imagine the Earth was doing something like that after this collision. The collision didn't hit it straight on, but hit it at an angle, which caused Earth to start spinning. And this is one of the coolest things I discovered in trying to figure out all of this. Let's see if I can get out of here so we can stop the share. Maybe you think that the Earth has always rotated at the same speed, 24 hours a day. And let's not get into the whole 23 hours and 56 minutes thing. You guys remember that? We're not going to get into that. But I discovered that the Earth's rotation is actually slowing down. This is great news for those of you who are procrastinators, okay? Literally, every day is slightly by microseconds longer than the day before. It's not going to help you procrastinate very much. I'm only kidding. But I do know that during the Jurassic period, which dinosaurs were famously dominating, the Earth's rotation made it so that a day was only 21 hours long. So think about that, 21 hours long. And since that time, the Earth has slowed down only enough to give us about 3 hours more in 100 million years' time. So just assume that this rate of slowing down is going to continue. Is it? Possibly. Could it be that the Earth slows down so that a day becomes far distant future 30 hours long, and then 50 hours long? And then for those of us who are really procrastinators, just dream of a day when the Earth has 100 hours per day and you can take your time. You have lots of time to do everything you need to do. So anyway, being silly here, but the speed of a planet's rotation has more to do with what was going on during the time of its formation than anything else. So Venus doesn't have a moon. Venus spins in the opposite direction that we do, and Venus doesn't even spin very much. It actually spins slower than it goes around the sun. So what if that was the Earth's rotation? What if Earth was like Venus, and then this collision gave us a 24-hour day cycle that we have now and a moon? So it's a cool thing to think about. It's one of those what ifs that you can always spend a million years going into about what would have happened if the moon didn't form? What would have happened? There's actually a book. I don't have it anymore. It was at the Fairbanks Museum for a while. Steve Molesky, our wonderful meteorologist, had bought this book and recommended it to me. It's called What If the Moon Didn't Exist? I don't have that book, but I would recommend, if any of you were really curious, it will talk about how the moon, not only does it give us beautiful light at night, it stabilized our orbit. It stabilized the tilt of our axis. And the moon may even play a part in why we have ice ages and other climatic shifts based on the Earth's orbit. So if the moon, oh, by the way, we wouldn't also have tides. If we didn't have the moon, there would be no such thing as high tide or low tide. So just think of how different Earth would be without the moon. Maybe, and this is what the book speculates, maybe life on Earth would not have even been possible without the moon being there to help stabilize this dynamic system. That's all speculation, but it's pretty cool to think about. The planet's rotation was given to them by things that happened at the beginning. There's even a Daft Punk song that says that in the lines, a Daft Punk song with the Pharrell sings, and it says, what keeps the planet spinning? A force from the beginning. And that's just a dance song. And I happen to love that song. But I just thought, oh, so cool that the lyric worked in something that's literally true for the history of our planet. So you could go listen to Daft Punk if you don't know, from that album, Random Access Memories. So great song. However, it's time to take a break. It's 3:58. Do you have a question coming in, Leila? I see your hand up. Does anybody have a question before we stop and stretch? Oh, somebody's been playing a lot of pool, huh?
That's what I was going to say.
Yeah. Well, now you could tell your parents, no, I'm not playing pool. I'm simulating the conditions at the formation of the solar system. That's what I'm doing. We call it the late heavy bombardment, when there was almost like a pool table at the beginning of a game, lots of stuff swirling around. Most of that stuff has found its pocket, and now the solar system is a much calmer place. But it's about 4 o'clock. I can't believe our last hour together this year is coming now, but please stretch, take a break, give yourselves about 5 minutes. I think just enough ice melted off the trampoline. I'm going to head out there. I'll see you guys in about 5 minutes.
Oh, that's cool. Look at all those tessellations. Wow. Look at MC Escher. Oh, these are all MC Escher. That's so cool, huh?
Yes, I muted myself by accident. But as you coming back, I mentioned the artwork of MC Escher, perhaps one of the greatest masters of optical illusions and definitely of tessellations. I mean, some of these are really cool. Like this is a melting tessellation. It goes from birds to triangles. How cool is that? Or some of these, like the one that goes from ducks to fish. You notice the negative. So if you want to have a cool form of art to get into, now just imagine if the Giant's Causeway had broken into Pegasus-shaped cracks instead of hexagons. Then you'd be talking about stuff. You'd be like, "Hey, Pegasus was here."
Wow. Look at the fish one.
I love this salamander looking one. Here's a cool one that shows you the underlying pattern. But when I think about art like that, I just think, how did this person see the world? You know, how did their eyes look like kaleidoscopes to them? You know, or just imagine the imagination that brought about these ideas. This one's so cool, a little Scottish Terrier schnauzer looking thing. There's no end to this. Oh, apparently there's a book called Tessellation with Kids. So I just searched in empty Escher tessellations just to give you guys something to think about. But I hope everybody's back now so we can resume, because I did not realize that all of those great questions from Rainy Rose were going to take up a whole hour, but that's because that was a really, really cool set of questions to ask. So I hope we have everybody's questions ready to be answered now. And I hope it's not going to take an hour per question. Unfortunately, we won't have that much time. But I do want to get to the question that I saw about the smiley face, Saturn, Jupiter, and the moon. So let me show you how to do that by getting back into Stellarium, and I'll show you the time, what we're talking about. So let's look at tomorrow morning first. So I'm going to speed up time in Stellarium and bring about the sunset. But we're actually worried about not the sunset, but what happens before the sun rises in the morning. So I'm going to orient ourselves to the southeast. I hope it's not too choppy with our internet connections. But all right, maybe I won't do it so gradually. I just get to it because I know that not all of you will be able to see a smooth animation. But we just passed midnight and we're heading into 1 in the morning. And by the way, there's Antares, not Mars. Now, what's that? Oh, that's a star. I'm just trying to see. I have labels off, so this is for me more fun because this is like the real sky. No planets are up yet, but I think one is about to arrive. Yep, there you are, buddy. Jupiter. Look at that. That's tomorrow morning, by the way. Jupiter will be rising at around 2:20. Your parents will not thank you for waking them up at that time. But look what's right next to it. Is this the eye of our smiley face? Right here, it's Saturn.
There's the
And then
do you see them?
a little bit later, Mars. Now, a version of this cool parade is going to be happening in the summertime. Remember the teapot of Sagittarius and Scorpius, that's going to be our summer sky. So when summer comes, maybe we'll be seeing each other again in the fall. These will be out in the evening. So right now you have to wait till 3:30 in the morning to see these 3 planets. But remember, right now is a new moon. So did that make a smiley face? Let's go to the date and time window. And let's go back one day at a time. April 23rd, tomorrow morning, April 22nd, April 21st, April 20th, the 19th, 18th, 17th, 16th, 15th. Oh, what do I see here? A crooked smile. You know what it looks like to me? It looks like that kid Finn from Adventure Time, puckering his lips like he's gonna give Jake a kiss. Instead of a smile, it looks more like, Can you see that? So I guess he looks like Finn from Adventure Time because Finn basically has 2 dots for eyes. So he looks pretty simple as a cartoon character. And so it wouldn't be right to say it was a smiley face, perhaps, but it did make a face-like thing. And the day before, I just wanted to see what would have happened the day. Oh, hold on. I went too far. The day before, the moon was way over here. So that would not have at all resembled a face. But that morning on the 15th, about a week ago, wait, that would have been the morning, I think, of the last time we met. But I guess I haven't been focusing on the morning sky only because I don't tend to be awake at 3:30 in the morning. I'm more likely to be awake because I stayed up that late than I am to wake up at 3:30 in the morning. That's for sure. So that's not something I had seen, but I'm glad you pointed it out because that means you're paying attention to these patterns. And that is the coolest thing. You're going to see that picture of Mars and Jupiter and the moon. That's going to repeat itself in some form or another every moon from now and through the fall. So next month, you can see it again. So did anybody else have a question? It actually did look like a smiley face. So Seamus is weighing in here. I'm glad you said that. So are you saying that maybe you just have a better imagination? Maybe was it more crescent and less fork?
It actually did look like a smiley face. It was pretty cool.
Okay. Hey, that you are free to imagine it however you like. But the fact that we're talking about this looking like a smiley face at all, imagine telling a robot that looks like a face. That is part of the human imagination. Have you kids heard of a word called pareidolia? I've mentioned it before. Pareidolia is the tendency for people to see faces in things that are completely inanimate. And there was a Pixar cartoon about 2 umbrellas that fell in love with each other, where the whole entire thing, all the characters were outlets, street lights, sewer covers that did not have faces, but looked like they have faces. And so they were smiling and interacting. And actually, Django, can you do me a favor? In the mudroom, in one of those Aubuchon bags, there's an electrical outlet. Can you bring one, the black one? I'm asking my son to give me something because pareidolia, seeing a smiley face in the sky, is one of the things that people do since they're little kids. And I remember when I was a little kid, thinking that every electrical outlet looked like a face. It looked like a shocked face, like a face of somebody who got electrocuted, like, oh! And I actually asked my son to bring me one because I have one here, a spare one that I was going to use in a project. Does that look like a face to you?
Yes. Yes.
A surprised, shocked face. Oh! So think of how humans can do that. That is how much our brain is oriented towards looking for a face, seeing one even when there is none. And that's something that goes back to when you're a itty bitty little tiny baby. And probably the only thing that you can see in sharp focus was one of your parents' face going, oh, you're so cute, you're so cute. Oh, look at you. So that might be the first thing you ever see in human life is a face or another body part, but mostly a face. Like, oh, are you hungry? Well, anyway, Good, good. But where are the rest of the questions? I want to hear from you guys. Do we have to go around the room, or so to speak, or can you volunteer them or even put them in the chat? Because
I have a question.
all right, birthday boy, what's your question?
Well, this one time I was going to wash my hands and my hands weren't quite wet enough, and neither was the bar of soap. I put soap on my hands and started rubbing them together, and then when I finished singing in ABCs, I still felt the soap in my hands, but I couldn't see it. So what happened? That's my question.
Well, soap, I mean, you don't have to see it for it to be there. I've had many times where somebody washed a coffee mug and left the soap in it, and I thought it was clean, but then I make coffee and I taste dish soap. It seems like somebody forgot to rinse all of it out. But soap is generally alkaline, and it has a chemical property that we give it to. Basically, it messes with that. Remember that whole thing about water sticking to itself, that whole surface tension concept that I mentioned when we were talking about water molecules? Soap disrupts that, and it allows, it kind of gets into molecules that otherwise would stay apart. For example, oil and water. Oil and water don't want to mix. But if you put soap on the oil changes on a molecular level that allows it to mix with the water, which is why if you have an oily plate and you run water on it, the oil stays on the plate. But if you put a little soap on the oil and then run the plate, you'll see that the oil washes off with the water, because it's like it got recruited by the soap into acting like water. Whereas before the soap was there, the oil repelled water. So I don't want to go into the whole concept of, fatty acids and polar versus non-polar molecules. But when you put soap on your hands, what you're doing is converting the oils on your hands, which don't want to wash off. Think of how oil and water don't mix. Your hand is covered with natural body oil, and your water washing it would not really remove it. It would just run right off of it like water off a duck's back. It would beat up and roll away. So if your oil on your hand had contaminants, a virus, a bacteria, dog poop, cat poop, toxoplasma gondii, whatever, if you have that on your hand, you don't want that to stay in the oils. So when you put a little soap on there, you basically turn the oils on your hands into something that does dissolve into water. And then when you rub your hands, the action helps the oil to break up and then flake off. And then when you rinse your hand, when you're done doing the scrubbing and singing whatever song is 20 seconds long, then the oils on your hand are stuck with the soap and the water and not stuck to your hand. This is also why when you wash your hands very hard, your skin feels really dry, because you've removed that oil and it allows your skin on the outside to desiccate. So this can cause your skin to get really rough. And that's why a lot of people like to use lotion. Guess what lotion is? Oil. So if you wash your hands with soap and water, you're removing your natural oil. And then if you get some Palmer's cocoa butter, or I don't know, oil of Olay, or I don't know, Jergens, whatever you might use at home, that oil that you put back on, it might come from coconuts, it might come from vegetables, it might come from soybeans. You're replacing it, and that helps trap the moisture. So it's basically like swapping skin. Oh, I got a contaminated oily skin. Let's wash it off with soap and replace it with a clean skin of new oil. Yeah, that's why my iPad has so many greasy fingerprints on it. Ugh. That's not lotion. That's just my natural oil. But if I had washed my hands and used lotion, the same result would probably happen. I'd be leaving grease all over the place. So that's how soap, and if you've ever made soap, Taylor, soap is made from oils, fats. How is that? How do you use something made out of fat to get rid of something made out of fat? It's because of the chemical change. When you make soap, you can't just make a bar of soap out of butter. That won't work. But if you take butter and you mix it with lye, sodium hydroxide, which is an extremely alkaline substance. If you remember acid like sulfuric acid is one of the most acidic substances in nature. And lye, sodium hydroxide, is on the other opposite end of the extreme. It's one of the most alkaline substances in nature. And if you add that to your fat, you've changed it from a fat to a soap. And that has the ability to basically break up other fats, because it's It's like a spy that, it hangs out, it knows how to hang out with fat, but it recruits them to the water side of things. Maybe I'm making a silly analogy, but kind of like what it is. So, and if you wanted to make soap in the old days and you didn't know how to get lye, sodium hydroxide can be made from ashes, from wood. So you can make soap with fat and ashes, something that's very ancient. So people have been making soaps since prehistoric time because you didn't need to know the chemistry to make it and to notice, hey, that stuff cleans my clothes. When I use regular water, my stains stay in the clothes, but now it comes out. So people discovered how that soap works long before they knew how it worked. And that's a lot of what chemistry is. People didn't know how it worked, but they just had the practical knowledge to make it. Well, anybody, please give me some more questions, guys, because I'm about to tell you something so gross. You're going to wish you had given me another question. But I just found out when I was in Rome a year ago that people used to, well, the Roman Colosseum, they didn't use it every day. But when they had a day when there was going to be a Colosseum event, a carnival festival with gladiators and all that, can you imagine how much urine came out of that Colosseum? Oh, Leila, I love the face that Leila is making. But yes, I actually saw the place where there was a trench that took all of they actually had urinals, just like at a modern baseball stadium. I swear, I could not believe this. They had little stands, they're still there, and they drained into a floor, into a common sewer that ran all of that urine and other stuff out of the Colosseum into an area that apparently, according to my tour guide, whenever there was a Colosseum event, the slaves that were in charge of doing all the laundry for all the wealthy people in Rome used that urine to clean the clothes because it was cheaper than using a soap. So it was like free laundry. And I'm very grossed out by this notion, but it's technically true that urine can help remove stains. But just imagine, like, if you're some wealthy Roman senator and you're like, I have got slaves at home washing my robes for me. They're always so sparkling clean. And then you find out that your laundry slave was using the urine from 70,000 random Romans to clean your clothes. Is that really clean? I don't know, but it got the stains out. So I told you you're gonna wish you had given me a different question to answer. But yes, so of all the things that people have used to clean stuff, let's just be glad that we have, I don't know, wonderful soap that smells like lavender instead of that to clean our stuff with. So come on, folks. I need questions from you. I have other things I can show you, but I was really expecting to have a lot of questions from all of these kids. So
Bobby,
please,
can I-
yeah,
Hey,
please.
Bobby.
Go ahead. Is that Marguerite?
Yeah. We were talking about it the other day. We'd read how the COVID-19 virus kind of dissipates in warmer weather and then comes back in the cold. And so like the Southern hemisphere is not experiencing it to the degree right now that the Northern hemisphere is. Why is that? Like, why does a virus I mean, I know it's partly to do with people being outdoors, but is there another reasoning behind that?
Well, it's actually kind of closely related to what we're talking about with soap and oil. So this is a great question to ask now. Okay, viruses as a physical body are basically a bubble. In the case of the coronavirus and a lot of virus, not every virus is this way, but the coronavirus and flu virus too, which is the one we have a lot more experience with, they have a jacket, the coating, the little sphere, the part that you see with all the protein sticking out of it, that sphere is mostly made out of fat. It's a lipoprotein. So it has the same properties as a fat, which means that soap will make it fall apart, and water. So this is why washing your hands is such a great way to get rid of coronavirus. You can't coat your lungs with soap to stop it from, infecting your lungs. If we could, then we would not have to worry about it anymore. So it's only dangerous if it's intact And anything that causes its shell to fall apart basically separates the RNA, which is the bad instructions that make the virus work, from the spike proteins. And the spike proteins by themselves can't do anything. And the RNA by itself has no way to get into a cell. So by breaking the outer shell of the coronavirus, you've destroyed it. It's useless as far as a virus is concerned. So what weather does to that is that viruses evolved to survive inside of a body that's actually hot, 98.6. So heat at that temperature doesn't really kill the virus, but what does kill a virus is drying out. Okay, so if you have a picnic table in the sun and you sneeze on it, your droplets of booger from your sneeze could have a lot of virus in it. But as soon as that starts to dry out, if the droplets evaporate, then the virus is sitting there in a desert. Think of that picnic table as a desert for a microscopic thing. And in that desert with no moisture, eventually the outer layer starts to crack and break. So it's an idea that maybe in warmer weather, this virus will have a harder time lingering in public spaces. So like if I sneezed in a public park in the winter, when it's cool, that droplet of water might spend hours before it evaporates and the virus inside of it gets brittle or broken. But if I walk through a public park on a hot summer day and I sneeze, that evaporation that might have taken hours in the winter might take minutes in the summer. So that's the thinking behind why some flu, like the flu, doesn't spread so well in the summer. But here's a couple things to consider. When we're in summer, half of the world is in winter. And there are plenty of places where it can be damp and moist all year round. So this idea that the virus might stop spreading in the summer is not a guarantee. It's not for sure. It might slow down in a local area, but if you have tourists traveling from another place where it's still flaring up, all of that will be negated. So we really don't know for sure whether or not coronavirus is going to transmit as easily during the summer or not. If you look at the list of countries where it's spreading, South Africa has a lot of cases, and they were in the middle of summer when they started getting it. So you see what I'm saying? They were in summer already when they came there, and South Africa has a lot of coronavirus. So it's not a guarantee that being in a hot climate is going to save you from this. The places in the world, the reason why so many countries in the hot part of the world have less coronavirus might be more to the fact that there's less travel in those countries. There's not as much wealth, and people don't generally go, to Italy for vacation and then come back home like Americans might be more likely to do. So there's two ways this can go. We might find out that during the summer, the virus does not spread well. And that doesn't necessarily mean good things, because I think from a social perspective, that might make a more difficult situation. If the virus slows down, people might say, oh, coronavirus is over. We're done. And then when fall comes back, we'll get hit by another wave of this virus. And then it will be like round 2 of this lockdown, which would be really terrible. I don't think anybody wants to see it happen again. So if the virus actually spreads just as easily in the summer as in the winter, that could be a good thing, because they will keep people paying attention to it and people will not drop their guard down. And then we won't have this surprise resurgence when the weather changes. So that's one of the two scenarios. I'm hoping that it does continue, only because that way people won't drop it. And I really think that we don't want to see coronavirus turn into a seasonal thing like the flu, where it whips its way around the world every year and it mutates so often that we have to make a new vaccine all the time. Remember, it takes about 1.5 years to get a vaccine going. The flu, we have to do predictive vaccines because they don't know for sure what the flu is going to be like when the vaccine comes out. So sometimes the flu shot is very effective. Sometimes it's less effective. We don't want to be doing that dance with coronavirus, because coronavirus is either 10 to 40 times more deadly than the flu. And I don't want this to become a normal part of life. So somebody asked how many. Oh, okay. Okay. I see all the questions are coming in fast and furious now. So, what do I know about geomagnetic reversal? Thank you, Sadie. Actually, while I answer that question, the USGS has a map that is live updated, showing you where magnetic North Pole is, and it's moving all the time. So just to get everybody up to speed onto what I'm talking about, let's see, I'm putting up the United States Geological Survey. They have a map that shows you, let's see. Well, I don't want to search for it now, but let me answer your question. The Earth's magnetic North Pole is not the same as the true North Pole. The true North Pole, based on the rotation of the Earth, which points at Polaris, nobody expects that to change anytime soon. That would be end of the planet type of destruction for us to flip over, you know, and all of a sudden we see the Southern Cross and Australians see the North Star. That's not going to happen. It would take a crash like the moon's formation to make that happen. Pardon me. All this talking wears out my throat. But the magnetic field is a very different thing. If you remember some of the stuff we talked about with electricity, electricity generates a magnetic field. And the magnetic field that is pointing north, actually the South Pole is the North Pole. I know this is confusing. The South Pole is a north magnet, and the North Pole is a south magnet, which is why the North Pole of a magnet is attracted to the North Pole. Remember, opposites attract. It's so confusing. But what if the internal magnet of the Earth flipped so that the North Pole was a North Pole magnet and the South Pole was a South Pole magnet? That would mean your compass would actually reverse the direction that it's pointing. And the compass that you have would suddenly be the red points south instead of pointing north. That can happen because everything we know in what's called paleomagnetism, there's a kind of geology where they take rocks and they look at the alignment of iron crystals within those rocks. And those iron crystals basically tell you, like a frozen compass, what direction was north and what direction was south when that rock formed. And because paleomagnetic samples have been done all around the Arctic and all around the world for years, we can see that the world's poles magnetically have flipped many times in the past. And scientists recently started noticing that the North Magnetic Pole, which is somewhere, I think, in Saskatchewan, it's not at the North Pole, it's in northern Canada, they noticed that it was starting to speed up in the movement across the landscape. And that implied that perhaps the Earth would have a magnetic polarity flip sometime soon. But this is all new to us because let's just think about the fact that the compass invented in China is only about 1,000 years old as a device. So if the magnetic pole had flipped 2,000 years ago, would anybody on Earth notice? Think about that. Nobody would have had a way to know. The only things that might have been affected would have been maybe migratory birds and some insects. Some scientists have shown that there are actually, this is a really cool thing about geese and other long distance migratory birds. They actually have some cells in their brain that have a high concentration of iron, and they are thought to be basically biological compasses. So if you're a Canada goose and the magnetic poles flip, what if you fly to Argentina by accident? That could happen. But eventually those animals would adapt. They would eventually figure out that, wait a minute, my brain compass is backwards, and some of them would get lost. Some of them would find the way, and eventually they would adapt. So I don't think it's something that would be the end of the world, but it would be really weird. But today, humans barely need compasses anymore. Today, we have so many other ways to navigate, like GPS, that would not be affected by this. So I don't think you need to worry about this, but it is a cool thing to imagine that the Earth's that dynamic, that the internal magnetic field generated by the swirling magma and the spinning metallic core and the metallic crust that surrounds it, all of our planet works like a giant electrical generator, and electricity is what generates these magnetic fields. But flipping it is not that hard as far as Earth is concerned. It's happened many times in the past. It's only now that there's a creature on Earth that cares, and that's humans. So that's one of the cool things. So is there any truth to the Myers-Briggs test? Is this Seamus? Seamus, the Myers-Briggs, that's the personality test that says like introvert, extrovert, right?
Yeah.
Okay. I actually took that test in college, and it said that I was a extrovert thinker. I think that's one of the categories, right? And that means that I'm probably going to be a politician or a serial killer or no, just kidding. I mean, I don't put a lot of stock in those kinds of things personally. I think that everybody wants a shortcut to figuring out how to evaluate a person. And the Myers-Briggs test is used by some employers on their future employees to find out whether or not they should hire somebody. But here's what I think about a test like that. There are so many aspects to a personality that I don't think a questionnaire can give it to you. Plus, if the people who you really need to worry about, like the people who might be dangerous and the negative kind of person that you don't want to have around, they probably also know how to give the right answers on those tests to give the right impression. You know, if you're a real sociopath, then you know how to answer those questionnaires to look good, while you might really be the joker lurking inside that seemingly friendly person. So that's why I don't take much stock in those personality tests. I believe that a perceptive person in a face-to-face interview, and you know, the longer you spend with somebody, the more accurate you can get this. But I think that you can get a lot more out of an actual talking with someone than you can through a questionnaire. But you know, I'm not a psychologist. I'm not a psychometrist, which is the people who do that actual thing, design psychology tests. But I have heard that a lot of people have mixed feelings about the Myers-Briggs test in that world. So I wouldn't worry about it too much. What did you get results? Why, Seamus? I have to ask because you must have taken it if you're asking me about it.
I'm an introverted thinker.
An introverted thinker.
Mm-hmm.
I believe that, except that you were probably one of the most talkative students I have.
Yeah,
I think you're more extroverted, at least from my perspective. I think you're more extroverted than that implies. But think of how many times you're the one raising your hand. I think a lot of our kids are introverted. I'll believe that amongst you. And I believe most of you are great thinkers. I think all of you are great thinkers. So, but that doesn't mean you can't be a feeler too. I would like to say that I could be both. I like to be a thinker, but I also like to be emotionally sensitive to other humans and myself around me. I'm not a robot. So I see, that's why I don't like personality tests, because I think everybody is a mix of all of those things naturally. But how many people can fit into the Coliseum? B. I admit, when I said 70,000 people's urine, that's what based on the number that I got, which is actually huge. That's bigger than most baseball or football stadiums today. And the only place I can think of that's actually bigger than that as far as capacity is also called the Coliseum in Los Angeles. The Los Angeles Coliseum was built for the Olympics in the 1930s. But because the Olympics, you know, have this connection with the Greek world and the Roman world is connected to the Greek world, they made a Coliseum in Los Angeles vaguely reminiscent of the one in Rome, but it actually was a quarter bigger, so it fit about 100,000 people. That was for the Olympics. And then the city of Los Angeles used it for other sporting events. And I remember the LA Raiders used to play there, and they had a big problem because that stadium is so big, it was hard to sell out the games. A lot of football stadiums are 50 to 60, 70,000 people today. That one's 100,000. But here's the coolest thing I learned about the Coliseum in that sense. The word vomitorium does not mean a place where the ancient Romans went to vomit. That is a historical misconception. But there is a structure called a vomitorium, and it's actually in every stadium. Have you ever noticed those big doors that are built right into the wall of the seats where people want to leave? They don't have to go all the way to the bottom of the stadium. They just go to the nearest hole and they go out through the back of the stadium. That is a vomitorium. So you may have walked through a vomitorium before. And the reason why they called them that is because it would allow the stadium to be emptied. So the stadium was the vomitor, and the stadium had to vomit out the people that were inside. And according to the history of Rome, there wasn't many times when they had to evacuate the Coliseum, but on the time when they did, on a sudden evacuation, when something happened like a fire, it took only 20 minutes to evacuate the entire Coliseum. That is the testament to the design of that place. It was built so well that you could get 70,000 people out in 20 minutes because everybody had a door close to them, a vomitorium close to them, and nobody had to go very far. And it wasn't like everybody rushing for one gate. The gates were big enough to hold the capacity of the people that were going to use it. So whoever designed the Colosseum back in ancient Roman times really did such a good job that we're still using all of those innovations to make stadiums safe today. If you look at a stadium design, you'll see the vomitoria all around the place. And then remember that from the Colosseum, you'll see them if you ever visit the Colosseum. If I could probably find my pictures of it, but you don't need my help to get pictures of the Roman Colosseum. There's tens of thousands online, easily found. And here's the funny thing I learned about the Roman Colosseum. This is not something impressive. This is actually rather sad. But there was a social hierarchy, as you might imagine, in the Colosseum. The people who sat closest to the ground, just like the people who can afford courtside tickets to the NBA games, are celebrities, rich people. And in Rome, it was the wealthy and the senators that all sat at the area closest to the action. And if basically you could estimate how wealthy someone was based on where they sat in the Colosseum. The lower level, if you were on the lower level, then all you had to do to escape was to run down the stairs near your seat and find a vomitorium close to you. But then there was an upper deck, just like stadiums today have upper decks and lower decks. And the upper deck was a lot scarier because if there was a fire or disaster, it would take you a lot longer to get out. You'd have to go through a lot of staircases before you left. And the upper deck was reserved seating for slaves and for women. So that's why I'm ashamed to say this, because the Colosseum, of course, was built in a time Roman society was extremely stratified, but women were held at the same level as slaves as far as attendance at the Colosseum events. And the only women that were allowed to sit at the lower level with the senators and the wealthy men were the Vestal Virgins, who were sort of like, not exactly spiritually the same idea, but conceptually similar to nuns. They were women who were devoted to the goddess Vesta, Hestia in Greek mythology, and they were sort of holy people in that time. And because of that, they were the only women that were allowed to sit with the senators and the wealthy nobles. But the real reason is because most of the Vestal Virgins were the daughters of the wealthy people. So really, it was just like they were sitting with their dads. So weird stuff in Roman history, but all that urine was a laundry soap too. So just think of all that the Colosseum. And I hope you guys give me some more questions, because I'm going to tell you some gross stories about the Colosseum, unless some of you can.
If we run out of laundry soap.
Yeah. Hey, in this time, maybe that knowledge somewhere down the road might be.
Thanks. Yeah, after the toilet paper goes, then we just can, yeah.
Yeah, we're going to be really do-it-yourselfers in that phase of life. But I just wanted to mention just another thing. Most people my age and younger probably think of ancient Roman Colosseum events as looking like what they saw in the movie Gladiator with Russell Crowe. That's probably the most popular movie of recent times that depicts the Colosseum. But I've also learned that movie did not fully explain things, and it exaggerated and sort of skipped out on things. Well, first of all, the word arena comes from the fact that the bottom of the Colosseum was made of sand, and in Spanish and in Latin, sand is arena. If you speak Spanish, arena is the word for sand, and that's the word arena. So they fought on sand, but it wasn't just sand. The sandy floor of the Colosseum was actually a wooden platform covered in sand, and underneath that platform was at least 24 wooden elevators. 24 elevators. They were trap doors and big contraptions that were, of course, powered by slave labor. Slaves would pull the ropes on pulleys and raise and lower things. And this is what my tour guide said: a typical day at the Colosseum would be an all-day event. And in the morning, they didn't have gladiators fighting yet. That was like prime time. That was the big event that happened in the afternoon. So the morning was occupied by executing prisoners in the most cruelly elaborate way imaginable. So I'll give you a hint. This is what my tour guide Marco Rossi told me in Rome. When they wanted to execute a prisoner, they would have somebody announce the name of the prisoner and the crimes that he committed, and then suddenly, within a blink of an eye, those trapdoors would open, and let's imagine a bunch of pine trees appear, literal, actual living pine trees in giant pots, shooting up out of the ground, and in a matter of seconds, the entire arena looks like a forest. And then they release a big brown bear captured in the mountains where those trees grew. And then they released a prisoner with some kind of meaningless weapon, like a hand pocket knife or a little tiny spear. And the entertainment was watching this prisoner running around the forest, trying not to get eaten by the bear. But of course, the bear would eventually win, and everybody would cheer. Yay! And then the forest would disappear. Poof, the trees would go down into the platforms. The bear would get hauled away by its handlers. And then palm trees would pop up through the ground. And all of a sudden, it looks like you're in the Sahara Desert. And instead of being chased by a bear, the next prisoner gets chased by a cheetah. And then everybody sees a cheetah tear this poor guy apart. So it was actually like a very theatrical executions. There was even one time where the Roman emperors, you know, they wanted to have a retelling of the story of Icarus. So they had a person dress up like Icarus with the wax wings, and they had this person climb to the top of a tower. And when the part of the story about Icarus not, you know, making it, crashing to the ground happened, that prisoner was pushed. And they plummeted with their wingsuit, and they landed on the floor of the arena, and everybody cheered. Woo! Why do we call that civilization? I don't know. But anyway, that the Roman times, they were able to build beautiful things that they used to do very ugly things. And that's what I think about when I study the ancient Romans. They did horrible things in beautiful buildings. Look at it that way. And so what if the prisoner somehow won? I actually asked that question, and there was no story indicating that ever happened. But I also wonder if the Romans probably wouldn't have wanted that story to get out. They didn't want anybody to know if somebody ever survived that. But the other thing about the arena was that it was surrounded by a fence made out of elephant tusks that were curved inward. So if the animal that was chasing the person got another idea and decided that, forget this prisoner, I want to eat that, you know, that very plump senator up there. He looks like more meat than this, you know, scraggly prisoner. The animals would not be able to leap out because they had a fence with inward curving tusks that was supposed to keep them from being able to do that. And if you look at the Colosseum, the floor was really far below where the first seats were. So there was something like 10 feet separating them. So the animals couldn't escape and the people couldn't escape. So there's only one way that story's going to end. What I want to know is if there was ever a day where the bear just gave up and sat down and the person sat down next to it and they were probably hanging out like, you know, Mowgli and Baloo. They would be like, oh, what are we going to do now? Send in another bear. This bear's too chill. So,
and what would happen if the prisoner just stabbed the bear and it died? How about this? You can try to find that story. And if you ever find a version of a story where somebody survived the cruel punishment, I would love to know. But just to finish the story, I don't want to spend our last time just talking about horrible things at the Roman Colosseum. But that was what happened before lunch. Then they would have lunch. And people sometimes actually cooked and barbecued with little grills in the Colosseum in their seats. So it's like a tailgate party in the stadium. People are cooking. I got sausages. Anybody want sausages? You know, and then there were probably people walking around selling food. It probably wasn't popcorn because they hadn't met the Native Americans yet. And it probably wasn't peanuts, but there must have been walking around selling, I don't know, fried pigeon. Anybody want fried pigeon? I've got some on a stick. And so it was a festive environment. And then she left us. Well, after the lunchtime, then the gladiators would come out. And think about, I don't know if you kids have ever been so into sports that you might collect baseball cards or football cards, like your favorite athletes. They have their little picture. If you know, even in Harry Potter world, they have that for Quidditch players, right? Where Ron has the cards for the different players. And in the Roman times, they did that with the gladiators. Each gladiator was a slave, but a famous slave. So they had fans. And I don't know, let's say Cassius the Savage was one of their names. I'm making that up. But Cassius the Savage had his fans and they would go and root for him. Cassius, you should win. Cassius, if you won, you survived. If you didn't win, you died. And the gladiators had costumes. They weren't just wearing armor and weapons. There were actually themes. Like one of the themes was to be like a fish. So there were gladiators that wore helmets that had fins on the top that were very sharp, and their armor had fins that were actually like blades. So they looked like a fish. And then the gladiator that would fight them would use a net and a harpoon, and he would look like a fisherman. So sometimes the gladiators themselves were wearing costumes that reflected different fighting styles, different skills, and it was very theatrical, like a Broadway production, but somebody dies. Very sad. And then there was a gate that all the gladiators would enter through at the beginning of the battle, and only the victorious gladiator would exit through that gate. And that was, you know, it was the gate that faced east, like the morning sun. If you went out through the east gate, that meant you lived to fight another day. And right outside of that gate was a giant fountain where all the gladiators covered in blood would wash off their wounds. So it's pretty grisly, but not like the movie Gladiator at all. Just imagine getting excited about that. Let's go watch a bunch of people die today. So let's say that we're way more civilized than the ancient Romans, who considered themselves to be the most civilized people on earth at the time. So, boy, somebody better ask me a better question or it's going to get even more gruesome.
Can I ask a question on a lighter note?
Please. I don't want to talk about any more Mortal Kombat. So,
a couple classes ago, I had mentioned that I had experienced a possible meteorite land 20 feet in front of us in a pond.
Yes.
It reminded me of this other pond, the same exact pond, a different experience I had there, where I was out canoeing one day and I looked into the water and I was surrounded by millions of tiny quarter-sized freshwater jellyfish. Is that something you've ever experienced before? Because I've never heard of it since.
Jellyfish in Vermont?
Freshwater. No, this is actually central New Hampshire.
Oh, okay. Wait, I have heard of freshwater jellyfish, but I had no inkling that they could be something that close to us.
Okay, I didn't either, and I've never heard of it since. So I was just curious if you had ever heard or seen them.
No, I am typing now just to Google it because I know that they exist. I'm just trying to figure out where the range is.
Yeah,
wow.
I know.
That is the craziest thing. No, they have them in upstate New York, so this is true. I mean, I'm not that I doubted you, but it's not crazy that happened. Oh man. So
it's pretty neat, but I've never seen them there again. It was like one summer and that was it. So I don't know how they get there. I don't know how anything about it.
Was it at night?
Nope, during the day.
Okay. Do you remember what season or month?
Oh no, I think it was late spring, early summer.
Well, I'm only guessing here. I know that in the ocean, jellyfish that are hard to find usually rise at night and go back down for the day. The freshwater jellyfish may have nothing like that kind of a life cycle or activity cycle. But what's weird is that what I'm reading is that they're found all over the world: Montana, Alaska, China, Russia. It's crazy how widespread they are, but they're only about an inch in diameter.
Exactly. They were tiny. And, I've worked in a lot of outdoor field work jobs and I've never encountered them again. So I was just curious if you had ever seen them.
So here's their name, Craspidacusta. That sounds like fun. Sower bee, Craspidacusta. And so, wow, I I went from today knowing that vaguely in the back of my mind there are freshwater jellyfish to now making this like my quest for the summer.
Good luck.
If I can find them around. Yeah. So, and you said it was in New Hampshire. Do you remember what lake it was?
It's called Pleasant Pond, and it's in Henniker, New Hampshire.
Henniker. Okay. I mean, I'm assuming that there's nothing unique about that pond. It probably has rivers that feed into it.
Yeah.
And like a lot of creatures, jellyfish, when they're babies, are nearly microscopic polyps. So they can get carried anywhere that water flows, which is probably why they're so widespread. Well, I'm so excited. I have another quest. Skunk cabbage and freshwater jellyfish that's going to define my summer exploration, I guess. But, I'm glad you brought that up. When you mentioned that, it made me think of something pretty cool. This is not the freshwater jellyfish, but another kind of story. Have you heard of an island country called Palau? It's a really beautiful country that looks like, imagine if Vermont got sunk into the ocean and all you could see was green mountains sticking out of the ocean. That's kind of what Palau looks like. It's either steep or it's wet. It's pretty much how it looks. So there's all these mountains, and in between the mountains are these lagoons that have become separated from each other. And because of the history of the ocean levels rising and falling, some of the lagoons have become separated from the ocean completely. So in Palau, there is a lagoon that used to be part of the ocean, now is a separate body of water that's still salty, but there's no connection between it. So creatures that are in there can't get back to the ocean now. And the jellyfish that actually evolved in that pond after they got separated from the ocean have lost their sting, have lost their venom. So there's a place in Palau where you can go snorkeling or scuba diving and swim through a cloud of millions of jellyfish without ever worrying about getting stung, because they don't have that ability anymore. And in that same pond, if you go farther down, there's a lake layer where the water is so filled with toxic things like cyanide that you will actually die if you scuba dive that far down. So that I saw an IMAX movie about that place, Palau. And when I saw that, I remember thinking, whoa, that seems like as close to being like on another planet as you can get while still being on Earth. So
did you say where Palau is? Is that?
It's in the South Pacific.
Okay.
I'm trying to find. I was going to try to find some cool pictures of Palau to share with you guys, because once you see, the landscape, you'll understand why it's such a cool playground for evolution. Because here's a perfect view. I'm going to share this with you guys. I just Googled Palau in Google Images, and there's a lady swimming through the jellyfish I was talking about.
There.
So that looks like you in New Hampshire, right, Christy?
Absolutely, yeah.
So a comparable image, except those look a lot bigger than the ones you described. Yeah. But it's in these pictures that you can see how this place has these little landlocked lakes that don't get in touch with the ocean anymore, although they used to. So that's actually kind of like why Charles Darwin liked the Galapagos Islands. Palau is a sort of a playground for nature's evolution, a place where a lot of new environments have been created recently, and you can see new species coming into existence right before your eyes. So maybe one day we'll have a class there. That's my goal. One day to maybe I'll be an old man, my bucket list. I'll get to Palau someday. So, oh no, it's 4:57. It's the last 3 minutes of one of the most fun things I get to do as an educator. I want to tell you folks, all you kids, that I teach a lot of people. I teach thousands of kids all year round, but the kids that are in this group are by far my favorite group of kids to teach, because you guys ask great questions most of the time, and you give me new ways to think about things. Sometimes your questions surprise me, and I have to think about things in a new way. So as far as a teacher, you kids are a challenge and a joy to teach. You make me a better teacher, and you make my teaching a lot more fun than it sometimes is. So I want to thank all of you, especially given that it's not that much fun to meet online as it is to meet in person, and the carnival atmosphere that we sometimes can create in our classroom is not the same on Zoom. But I really am grateful for those of you who still stuck with it, and I hope that the stuff that I've taught you is just the beginning of you continuing to explore all the amazing things that we can learn in science and in nature. Because really, science is nothing more than the appreciation of what's going on in the natural world. It is to pay attention to stuff that other people might ignore, and by paying attention and noticing and observing, you could discover things that save the lives of humans for countless generations. Think of Louis Pasteur, okay? Think of Rosalind Franklin discovering the shape of the DNA molecule. Think of Eratosthenes calculating the size of the Earth. Oh, I'm still talking about him 2,200 years after he died. So science is something that connects us with people who lived thousands of years ago. It connects us with the generations that haven't been born yet. And I hope, that you, even if you don't become a scientist, that all of you continue to think scientifically and observe and appreciate how amazing it is just to exist in this universe. So, anybody have a last question? Because this is your last chance.
I have a question.
All right, birthday boy, what is it?
Is Fairbanks Museum gonna have a science fair?
Not this year. Like so much of our world, everything is being postponed or canceled. So we, just like how the school year for the public school kids is, not going to continue in the buildings, we're going to follow those same guidelines from the state. Just like any other business or organization that deals with the public, we're going to follow all the strict guidelines. And the next time that this decision will be made by the state, there's going to be an announcement on May 8th. So that's just about 2 weeks from now, about what's going to happen for fall semesters of schools. And that's going to be when we can say whether or not we're going to be able to have classes at the museum. So tune into the news, listen to the updates from the state, but you'll be able to find out from the Fairbanks Museum's website. We'll be putting it out there as soon as we can. Just like anybody, we are desperate to get back to what we do. We want to have people visit the museum. We want to be able to do the fun camps and lessons in the planetarium. That's why we exist. What we're doing now is a good, meaningful substitute, but it's not the same. And we all want to get back to hanging out with each other, having ice cream, and looking at polar bears and looking at the stars in the planetarium. And just like everybody in the world, I can't wait so that when we can do it. But I'm happy to wait, knowing that just by sitting at home and not going out, we could be saving lives. You cannot stress that enough. I don't know. I hope you kids don't follow the daily numbers, only because it's quite sad to see how many people's lives have been lost. But what I want to say is that all of us sitting at home have prevented tragedy. There are thousands of people alive right now who did not get sick because all of us are staying home. So that's the good news. The good news that doesn't make a sound is that lives are saved quietly by us staying home. The bad news that does get a lot of attention is how many people have died. And since this thing started, feels like 5 years ago, it was only 2 months ago, it was originally something that was more affecting other countries, and we were just starting to get it when we first started talking to you guys about it. But today, the United States is the home of coronavirus, the COVID-19. We have over a quarter of all the cases in the world. We are unfortunately number one at catching this sickness. So that's why I want to make sure that you keep it up. Everything that you've been doing, like if you've made yourself a fancy face mask or washing your hands, staying 6 feet away from people in public and trying to keep yourself from spreading this disease, we're not done yet. We still need to do it for maybe as long as we've been doing it, maybe twice as long as we've been doing it, but it's so worth it. Okay. It really saves a lot of lives. So It stinks, but it's much worse than seeing our neighbors, pass away unexpectedly. So anyway, I don't want to end it there, but all of you, remember that this is not the end of our relationship as a teacher and student. You always can email me. And if any of you have questions, I'm available and I'll try to answer them as quickly as I can for whatever scientific inquiries you have. And specifically to Rainey and Rose with the telescope, don't hesitate to contact me if you need help with that. And if anyone else wants to borrow a telescope, send me a note. But don't hesitate me, getting my help, because I'm happy to help you through whatever you might have with the telescope, even if it's while you're using the telescope at night. I stay up late. I don't care. So anyway,
Yeah, thanks.
yeah. So, but to all of you, I wish you all the best, and I hope I see you all again in the future. If those of you who don't return for another year, I hope you take what you've learned and do something great with it, and let me know. Let me know where your journeys take you. Send me a jellyfish from Palau.
Thank you, Bobby.
Thank
Thank you so much.
A big virtual hug to all of you.
Bye.
And thank
Happy
you
birthday,
guys so
Taylor.
much.
Happy
And thanks to
birthday.
Leila.
Bye.
I want you to thank Leila too, because I know that I do the majority of the talking, but this wouldn't work if it wasn't for Leila.
Thank you,
keeping
Leila.
the notes organized and keeping the emails organized and doing all of the things, basically everything that happens outside of the time we're together. We can thank Leila for it because she's really on top of it. So thank you, Leila. And I want everybody to thank her too.
Thank you.
Thank you, Leila.
Thanks a lot, Leila.
No problem. Thank you.
Thank you, Leila.
Thank you guys
Thank you,
for joining
Bobby.
us.
Thank you.
All right, everybody, stay safe. Well, and
Bye, guys.
a day in the
Guys,
future.
Great day.
Ice cream day is coming.
Happy jellyfish hunting.
Yay.
Yeah, thank you, Christy. I will. I'm excited to go find them. I have a paddleboard just built for the purpose.
Perfect. All right.
Bye.
Thank you, Leila. Thanks, Bobby.
All right, take care, everybody. Be well.